Hello, everyone. Please take your seat. I'd like to introduce Kavya Joshi. She's going to talk about Gevent. So please give a big hand for Kavya.
Good morning. My name is Kavya, pronounced like caviar without the R, or caveat without the T if you prefer. And today, I'm here to talk to you about Gevent, which is a Python library for asynchronous I/O. More specifically, I'm here to tell you about how Gevent works under the hood. But before we do that, there are two important questions to answer. First, what is asynchronous I/O and why do we care about it? And second, what is Gevent specifically and why do we care about it? To answer both questions, let me tell you a story. Once upon a time, in a land far, far away, life was simple, and you could run a service to download Facebook photos and do something with them, display them in some funky way later, with a simple program that did just this. You fetched the photos from Facebook over the network, and you stored them locally and displayed them later. You can imagine the code for such a program is also pretty simple. Your function, download photos, opens a connection to the server, downloads the photos, and saves it. So far, so good. But then life got complicated. Your service exploded. Your user base grew to hundreds and thousands of users, and suddenly you had to do this for all of them. I hope you see what the problem is. The problem is the network request, the blocking HTTP request. The big problem with this implementation is that for each user, you're going to open a connection, send a request, wait for it to complete, and then proceed to the next user. It's just not scalable. Now, there are a few standard ways around the problem. There's multiprocessing, there's multi-threading, there's event-driven programming using libraries like Twisted, Tornado, Async Core, and then there are green threads. Let's understand each of our options. First up, multiprocessing. This is what your server program would look like under multiprocessing. For each user, you spawn a new process to run the download photos function. Now, each network request is still blocking, but it only blocks the process for that user. And so the end result is your program is still concurrent in terms of network requests. Now, this solution gives you the desired concurrency. In addition, it gets you parallelism, or the ability to take advantage of multiple cores if you're running on such a machine. But processes have a high overhead, so the solution is super unscalable. Which brings us to our next solution, multi-threading. In multi-threading, the idea is the same, where you spawn a thread for each user. And the good thing about threads is that they're lighter weight than processes. And so in general, this is a better concurrency model than multiprocessing. The problem with threads, though, is, as any of you who've done multi-threaded programming knows, multi-threaded programming is hard. Writing correct code is difficult, and debugging incorrect code is even harder. The second problem with this solution has to do with the fact that our far, far away land is called CPython land. And you've heard about the GIL. I won't go into detail because I hear talking about the GIL is so passé. But if you're interested in the gritty details, I encourage you to check out David Beasley's excellent talk on the topic. Now for our third solution, which is event-driven programming using Twisted, Async Core, etc. Now, event-driven programming gives you the desired concurrency, and it gives you the desired concurrency in a manner that's scalable. But the big problem with it is the code. It's complicated. In fact, the code is so complicated, my example didn't even fit into the slide because you have to run the event loop, you have to register callbacks into the event loop, and if you've heard of callback hell, that's all very real. Which brings us to our fourth solution, green threads. By show of hands, how many of you have heard of green threads? Whoa, awesome. Way more than I was expecting. But if you've heard about green threads, you know they're great for a lot of reasons. First of all, they're user space. The operating system does not create them or manage them. Secondly, they are cooperatively scheduled, which means that the operating system does not even schedule them. And the fact that they're cooperative means that they cannot be preempted. They have to explicitly yield control to one another. As a result of both of these two, they're extremely lightweight compared to threads. How lightweight are we talking? Well, with green threads, you can handle about 20 to 30,000 concurrent connections, no problem. That's impressive. And that's something that threads in Python just doesn't give you because of the memory overhead. Now, green threads are the concurrency construct that Gevent gives you. Gevent calls them greenlets, and this is how you'd use them. Now, the thing to note here is that the Gevent solution reads as simple as the solution with threads or processes. The API exposed is a synchronous API. But what I've just told you is that Gevent's greenlets are also extremely lightweight, which brings us to the question, how does Gevent provide this execution unit, this greenlet, that gives you the desired asynchronous I/O, but is also lightweight and so simple to use? I certainly thought it was amazing, and that's why I'm here giving this talk. And that brings us to the next half of the talk. We will first learn about Gevent's core building blocks, the greenlet library and the libev library. We will then learn about how Gevent integrates them or ties them together, and then we'll do wrap up and Q&A. Now, in the world of programming, the best way usually to answer the how does X work question is to go to the source code. Luckily for us, Gevent is open source. It's on GitHub, so that's exactly what I did. And this is what I saw. When you call greenlet, this is what happens. These are lines from the greenlet.py file. Well, let's see. Greenlet seems to inherit from a small g greenlet, which is imported from elsewhere. What's going on? Well, Gevent's greenlets, the big G greenlet, are built on top of, are an augmented version of the small g greenlet, which comes from the greenlet library. So let's ask again, what are the small g greenlets and how do they work? Here's a simple example to help us understand. Here I'm using the greenlet library directly. I create one greenlet. I create another greenlet. This is what those greenlets do. They call to print functions. And then to start the execution of this program, I'm going to call greenlet.switch. To understand what switch does, let's actually run through the code. So greenlet1 switches into the greenlet that's running print red, so we start to run it. We hit greenlet2.switch, which switches into the blue greenlet. So that runs, and we print blue, and then we hit greenlet1.switch. Now this is where it gets cool, because the second time we hit that line, it doesn't restart the function, it just resumes it, and so we get red done. Let's take a second to see what happens. Basically, what .switch did is it paused the current greenlet and yielded control flow to the next greenlet. And the next time you call switch, it resumes, it picks up execution rather than restarting it. This might look familiar to some of you because these are just coroutines. Now we understand the what question. What are the small g greenlets? They're just coroutines. Now for the how. How do they work? Now the greenlet library is written in C, and it's available as a C extension module. The fact that it's written in C is extremely important to how it works, because it works by manipulating the C stack. A little background on the C Python interpreter. In CPython, the interpreter is a C program. It's a C virtual machine. And so there are two stacks. There is the notion of the interpreter stack, which is the machine stack, or the C stack, also called the program stack. And then your actual Python code and Python call frames live on the interpreter's virtual stack, called the Python stack, which is not the real stack. So in this case, we're talking about the C stack, the actual machine stack. Cool, let's see how it works. So first things first, when you create a greenlet with a run function, it allocates a struct on the heap. You can think of this as a container for the greenlet state. At this point, it has a run function, which is the function you want it to run, and it has a parent. Every greenlet has a parent, and that's all you need to know at this point. Now, when you call greenlet1.switch, and this is your C stack, what happens is the current stack pointer is saved away in the greenlet struct. And then your greenlet1 starts to run. Then you call greenlet2.switch, and two things happen. The current stack pointer is saved away as the greenlet1's like its endpoint where it stopped running, and it's also saved away for the blue greenlet. And then greenlet2 starts to run. Then you call greenlet1.switch again. And this is where it gets mad impressive, so stay with me. What we need to happen is we want that's the slice of stack between the current stack pointer and the pointer that greenlet1 left off at. We need to resume or reclaim that slice of stack so greenlet1 can resume its execution. Now to do that, Greenlet uses a neat technique called stack slicing, which is implemented in assembly. And what it does is it takes that slice of stack that we need for greenlet1 to continue, and it just copies it off to the heap. Then it resets the stack pointer to the point where greenlet1 left it off, and then greenlet1 can continue execution. Let's take a second to appreciate what happened. We just changed the stack from under the Python interpreter's nose. It has no idea that the stack switch just happened, and it just continues execution. If you don't think that's cool, I don't know what is. Cool. So that brings us to the end of our first building block. Gevent uses greenlets to get these lightweight cooperative execution units in the form of greenlets, coroutines. Now let's go back to our Gevent server program. We understand what that first line does. Now let's look at what that second line, g.start, does. For that, we go back to the source, and hey, there's a loop. It's an event loop. Gevent uses libev, which is a high-performance event loop written in C. For those who are not familiar with libev, libev essentially gives you an API to register event handler callbacks. So if there's an event you're interested in, like a file descriptor being, like a socket file descriptor being read or written to, a certain timeout occurring, you can register your interest in the event and give it a callback. libev's event loop takes care of watching for these events. The way it does this, depending on the particular event, is in the case of socket file descriptors, which is what we care about, it uses kpoll, poll, kq, whatever is available. And then when these events occur, it calls your registered callbacks. Now, say for example, this is what you want to do. You want to say, hey loop, wait for a write on this socket and call my callback when this happens. This is how you do it. First, you have to make your socket non-blocking. The difference between blocking and non-blocking sockets is non-blocking sockets don't block, whereas blocking sockets do. So in the case of a blocking socket, your program actually It's the difference between saying wait till an event occurs on the socket versus throw an exception. The exception thrown is like event not available, I think, or something along those lines, and moving on with your life. Whoops. The second thing you do is you'd register your interest in the event by calling loop.io watch and giving it your callback function, and then you run the loop. Now, when you run the loop, this is pretty standard of event loops. They block the process waiting for these events of interest, and then when they occur, they call the pending callbacks. Now, libev adds 2 steps to this loop, which allows you to customize the event loop. Before blocking the process, it calls pre-block watchers, and after blocking the process, it calls post-block watchers. Now, the names are not important, but the idea is powerful. What this allows you to do is it essentially gives you a hook to integrate other event mechanisms into your event loop. What event mechanisms, may you wonder? Well, for example, if you care about integrating coroutines into your event loop, this is one way to do it. You basically change the statement to, hey loop, if there are coroutines waiting to run, if they're ready to run them first, and then block. And that brings us to the end of our second building block, libev. Gevent uses libev for an event loop. Now, if we go back to our server program, we notice that there are no explicit switches, and there are no explicit loop.runs. But we do know that there are greenlets, and there's an event loop under the hood. And that brings us to the second half of our story, how Gevent ties them together. To do that, let's dig a little deeper into the source code. Now, this first line instantiates a small g greenlet, and it sets its parent to the special and very important hub greenlet. The hub greenlet is special and important because it's the greenlet that contains and runs the event loop. There's one hub greenlet or one event loop per thread. Basically, when you call greenlet, when you instantiate a greenlet, it creates the 2 building blocks. It creates the small g greenlet to run your download photos function, and it creates the event loop. Now, let's look at what that second line does in closer detail. When you call g.start, it registers your greenlet's start or resume function, its switch function, into the event loop. And it registers it as one of those pre-block watchers. Now, remember what the pre-block watchers did? They were called before the event loop blocked. So basically, the .start function allows you to say, hey loop, this coroutine, the coroutine that's going to run download photos, is ready to run. Run it before you block. So now, at this point, we have our greenlet and our event loop set up, and we've registered one into the other. All we have to do is run the damn loop, and that's what this next line does. Gevent.joinAll runs the event loop. There are a few other ways to run the loop, and we're going to look at a simplified version, which is g.join. What this line does is it switches into the hub greenlet. When you switch into the hub greenlet, its run function is set to be the function, it is set to run the event loop. So basically, what we've done is .join runs the loop. It puts things in motion. What exactly does it put in motion? Let's quickly walk backwards and see how this all works. .join will run the loop. The loop will call all pending pre-block watchers namely your greenlet switch method. And then download photos is called. So what we've seen is that the hub, which is a Gevent construct, helps you tie together the greenlet and the event loop. Now, all of this is well and good, but it still doesn't answer our big question. How does using Gevent give us asynchronous I/O? Because the big problem is, when you call download photos, guess what? It's still going to make a blocking network request. Well, let's see. We have an event loop. Can we leverage it in some way? Why, yes, we can. And thanks to Gevent, we can with one line. Gevent monkey patches or replaces parts of the standard library. So calling that line automagically under the hood replaces socket with Gevent's version of socket, which is cooperative. Specifically, what Gevent's version does is when you create a socket, it makes it non-blocking for you. And then when you call socket functions like send or receive or accept, it registers it into the event loop, and it runs the loop. And that answers the how does Gevent give us asynchronous I/O. A large part of it comes from this technique called monkey patching. Cool. Now that we understand, or mostly understand, how our Gevent server program works, let's quickly run through it and make sure we have all the pieces down. Assume for this purpose that we have 2 users. Now, at the end of this loop, we have an event loop set up with pre-block watchers set to greenlet 1 and greenlet 2's switch methods. Then this line switches into the loop. Since we have pre-block watchers, we call one of them, and so we switch into greenlet 1, and we run the download photos function. Now, this download photos is going to make a network request. This is where the monkey patching kicks in. So it sets up the I/O watchers, and it switches back to the hub. Now, we're in iteration 2 of the event loop. There's still one pre-block watcher, so we switch into greenlet 2, repeat. Now, in iteration 3 of the event loop, there are no pre-block watchers left. So now the loop actually blocks for I/O. Now, say there's an event on socket 1. So our pending I/O watchers is greenlet 1. So we switch into it, and greenlet 1 resumes download photos. Sounds like asynchronous I/O to me. Cool. So that brings us to the end of our talk. To wrap things up, I want to make note of a couple things. First of all, Gevent, amazing as it is not perfect, nor is it ideal for all your I/O problems. It has a few shortcomings. First of all, it doesn't give you parallelism. Secondly, non-cooperative code will block your entire process if you're not careful. What this means is C extensions like database drivers are not directly available. You have to use the pure Python versions, which can take advantage of monkey patching. Secondly, compute-bound greenlets will also cause problems. So if you have a greenlet that's just running some CPU-intensive number-crunching algorithm, unless you insert these gevent.sleeps to make it explicitly yield, that one greenlet will hog your CPU. You can also use greenlet blocking detection tools. And thirdly, monkey patching may have confusing implications, like the order of imports matters. And we can talk about this if you have questions. That said, for the workloads that Gevent is a good solution, it's an excellent solution. We're talking about I/O-bound apps that need to be highly concurrent. In lots of benchmark tests, Gevent successfully handled 20 to 30,000 concurrent connections, which is hella impressive. And it is, in fact, used at web scale at companies like Pinterest, Facebook, Mixpanel, PayPal, et cetera. And that brings us to the end of our talk. I hope you've gained an understanding and an appreciation for the ingenuity of Gevent and how it takes greenlets and the libev event loop and integrates them using the hub and monkey patching. Thank you.
Okay, thank you, Kavya. If you have questions, we have a microphone over here. We have 2 or 3 minutes left. So if you have a question, please come to the microphone and ask. Yes, please.
Yes. Is it working? Yeah. So thank you for your talk. I appreciated it. I was just curious if there are any major functional differences between Gevent and Eventlet.
Can you speak up a bit?
Are there any major functional differences between Gevent and Eventlet, or reasons that you might want to choose one over the other?
Yeah, so greenlet, which is what Gevent is built on top of, came off of Eventlet. And I believe that it makes certain optimizations with the stack slicing, with the stack switching. I'm not too familiar with the details, or I don't remember them rather, but there's an excellent thread between the creator of Eventlet and greenlet that is available on the internet if you want to read up on it.
Okay. Thank you.
Thank you. I was curious if it was possible to combine multiprocessing and greenlet so that you could have one event loop per CPU on your server.
So as of Gevent version 1.1 that came out earlier in May this year, it might be possible to do so. In the previous versions of Gevent, because of the monkey patching and its interaction with the multiprocessing module, it was more complicated to do.
Cool. Thank you.
Yep.
Hey there. Hello?
Yep.
Do you have any recommendations for greenlet blocking detection tools?
Yeah. So Nihilus, which is the company I work at, uses greenlet heavily. And the sync engine repo, the Nihilus sync engine repo, is open source. And we have a snippet in the instrumentation.py file or the profiling.py file. And you can just use that code snippet as is. What it does is it spawns a POSIX thread, a monitoring thread, and then it uses greenlet's set to trace.
Interesting.
Yeah.
Cool. Thank you.
You can get the entire code snippet online. Yeah.
Okay, 2 more questions.
20 to 30,000 concurrent connections, the hardware and a source for that, and what kind of workload?
Great question. So the specific benchmark was a standard like Apache bench for HTTP servers, where you had a web server, a simple HTTP server which served something over the network. What was the second part of the question?
Do you have a source for it, the article / the analysis?
Yes, there's a blog post by Mixpanel from 2010 that performs this comparison. And more recently, as of 2012, there's another blog post that David Beasley has left a few intelligent comments on as well.
All right, thank you.
Hi. So earlier you showed that there's a pre-block watcher and a pending block watcher. So how does Gevent choose between which one to pick on? So how does the Gevent implementation choose, like, hey, because you have both items in the pre-block and the pending block, so what Gevent will choose from which one first?
Once it starts a new iteration of the loop, it'll always run the pre-block watchers first.
Okay, so if I have like millions of items in the pre-block, and there's another set in the pending block, so the pending block will have to wait for the Gevent to consume everything from the pre-block first.
Yes, and that is a problem that you do see if you spawn lots and lots of greenlets and don't run them soon enough. Because what that does is it grows the pending queue and the pending count, and that's exactly the problem you see.
I got it. Thanks.
Okay, thank you, Kavya. Please give a big hand. The next session will start at 12:10.